Hey everyone and welcome. We are absolutely surrounded by AI right now. Chatbots, image generators, the whole shebang. But what does any of this have to do with physics? Well, as it turns out, a whole lot more than you'd probably guess. The answer involves magnets, quantum fields, and a Nobel Prize that was maybe awarded for the wrong reason? Or was it?
So, it all really kicks off with this kind of a wild question. This year, 2024, the Nobel Prize in Physics, let me say that again, physics, was given for discoveries in artificial intelligence, not computer science, physics. So, how on earth did the study of algorithms of all things end up winning the highest prize in the study of the entire universe?
All right, to really get to the bottom of that, we've got to go back. We need to understand the people who actually got this prize. So let's jump back a few decades and meet the folks who really started all of this.
Okay, so back in 1982, a physicist named John Hopfield has this major breakthrough. Fast forward more than 40 years, and that work, along with some key contributions from Geoffrey Hinton, lands them the Nobel. But the real story, the reason it's a physics prize, it doesn't start with computers. Nope, it starts with something way more fundamental.
Yeah, this whole amazing connection, it doesn't start with silicon chips. It starts with a simple chunk of iron. So let's follow this incredible idea's journey, all the way from magnets to memory.
So way back in the 1920s, physicists were scratching their heads over a pretty basic question. How does a plain old block of iron become a magnet? To figure it out, they came up with this thing called the Ising model. Now just picture a grid, like a checkerboard, but made of atoms. And each one of these atoms has this little property called spin, which can basically point either up or down.
Okay, but this grid of atoms, it's not just sitting there frozen. Heat is constantly making these little spins flip around, randomly. But, and this is where the magic happens, nature is, well, it's kind of lazy. Spins that are next to each other actually prefer to line up in the same direction, because that's a lower energy state. It's more stable. It takes less work. And over time, it's this collective laziness, this desire to chill out, that causes the whole system to settle down, and boom, you've got a magnet.
And this gives us this brilliant analogy, the energy landscape. Just imagine that every possible arrangement of those spins, every single combination, is a point on a huge mountainous landscape. The system, it's like a marble you just dropped on that landscape. What's it going to do? It's going to roll downhill, right? It's always looking for the lowest valleys. And those valleys, those are the most stable, lowest energy states.
And this is where John Hopfield re-enters the story. It's 1982, and he's looking at this physics model of a magnet, and he has this just incredible light bulb moment. He thinks, okay, wait a minute. What if, instead of atoms with up or down spins, what if you had a grid of artificial neurons that were either active or inactive?
And the parallel here is it's perfect. It's almost one-to-one. The atoms from the physics model, those are now your artificial neurons. The up and down spins, that becomes the active or inactive states of the neurons. Even the strength of the connection between the atoms has a perfect analog. It's the weight of the synapse that connects the neurons. So the system is still trying to find its lowest energy state. It's still trying to roll into a valley. But, and this is the absolute genius of it, that stable, low energy state, it doesn't represent magnetism anymore. It can represent a memorized pattern.
So by changing those connection weights between the neurons, what you're really doing is you're playing God with that energy landscape. You're sculpting it. You can literally dig these deep wells around specific patterns that you want this network to remember. Then, when you show the network just a piece of that pattern, some incomplete info, it's like you're putting that marble on a hillside, and what does it do? It just naturally rolls down into the nearest, deepest valley, completing the very pattern it was taught to remember.
And just like that, it was a complete game changer. By borrowing the language of physics, of magnetism, a brand new path was opened up. A machine could now be taught to find stable states, to complete patterns, to remember. And for the very first time, using the same basic logic that makes a magnet work, a machine could actually truly learn.
But believe it or not, that connection, as mind-blowing as it is just the start. The story takes an even stranger turn now. We're leaving the world of classical physics and magnets behind and diving into the weird, cutting-edge world of quantum mechanics. And we're about to find an even deeper link between AI and physics. Okay, so let's think about a neural network in a slightly different way. It takes in some data, it does its thing, and it spits out an answer. You can actually think of this whole system as a mathematical field. Kind of like a weather map that has a temperature value for every single point on the map. In this case, the network assigns a value to every possible input.
All right, now here's the fun part. What happens if you make these networks ridiculously, incredibly wide? I mean, with just tons and tons of neurons. Well, back in 1995, researchers discovered something really surprising. As you make the network wider and wider, its output, its behavior, it starts to follow this very specific statistical pattern, the good old bell curve, what's known as a Gaussian distribution. And this was a really big deal.
And this is where things get truly wild. Physicists saw this result and their jaws just dropped. They realized this pattern was identical to something they work with every single day, the simplest possible model of a quantum field. See, a quantum field that has no interacting particles in it also has random fluctuations that perfectly follow a Gaussian distribution. The takeaway here is absolutely stunning. An infinitely wide neural network doesn't just look like a fundamental quantum field. Mathematically speaking, it is one.
So let me be super clear about this. This isn't just some cute surface-level similarity, no. This analogy goes all the way down. The complicated math you have to do to correct for a real AI, one that isn't infinitely wide, looks exactly like the math physicists use to correct for particles bumping into each other and interacting. It is literally the same mathematics.
Okay, so what's the upshot of all this today? Well, this deep, shared language, this shared math, has created this incredible feedback loop between AI and physics. They're now in this dance where each one is pushing the other forward in amazing new ways.
I mean, right now, AI is an absolutely essential tool for physicists. We're talking about AI that can clean up the incredibly faint whispers from colliding black holes. They're mapping the invisible dark matter that's holding entire galaxies together. They're digging through literal mountains of data from particle colliders, hunting for brand new discoveries. You could almost say AI has become this powerful new kind of microscope for seeing the parts of the universe we could never see before.
And you know what? It's a total two-way street. Physics is giving us the tools to finally peek inside these incredibly complex AIs, which, let's be honest, can feel like these impenetrable black boxes. Ideas like those energy landscapes we talked about, they help us actually visualize how an AI learns. And get this, we can now use tools straight out of quantum field theory to study the neural networks themselves. It's amazing.
So there you have it. It really boils down to two deep, profound connections. The first one, born from the simple physics of a magnet, gave us a blueprint for how a machine could learn. And the second one, coming from the strange depths of quantum mechanics, shows us that the way our most advanced AIs behave actually mirrors the fundamental fabric of reality itself.
And all of this leaves us with a pretty massive question to chew on, doesn't it? We've seen that AI isn't just some tool that physics uses. In a very real sense, it is physics. It runs on the very same mathematical principles. So you have to wonder, if AI truly speaks the same language as the universe, what other cosmic secrets is it going to help us translate next?